Welcome back, everyone. Today we're going deep on aircraft systems. Buckle up because it's going to be a wild ride.
Yeah, even if you aren't training to be a pilot, it's amazing how much goes into getting a plane off the ground and back down safely.
Right. We're talking everything. Engines, propellers, pressurization, de-icing, you name it.
You might be surprised at how much engineering ingenuity goes into it all.
Hmm.
It's a fascinating look at the physics of flight, too.
All right, let's dive right in. First up, the heart of it all, the engine.
Right, we'll start with reciprocating engines, the workhorses you find in smaller aircraft.
Okay, reciprocating engines. Remind me, what are those again?
They're like your car engine. They convert chemical energy from fuel into mechanical energy that drives the propeller.
Ah, okay. So fuel in, power out. What's the process behind that?
Well, it all starts with pistons. Moving back and forth inside cylinders. They turn a crankshaft, which ultimately powers the propeller.
Okay, so it's that piston action that gets things moving. Makes sense.
Yeah, it's a beautifully orchestrated dance of mechanics, really.
Now, are there different kinds of reciprocating engines?
Yeah, there are two main types. We have spark ignition, which is your classic car engine setup.
Okay, spark ignition. So like a spark plug ignites the fuel and air, right?
Exactly. And then there's compression ignition. You might know it as diesel.
Compression ignition, so no spark plugs.
Right. The fuel-air mixture self-ignites under pressure.
That's pretty cool. I didn't know they use diesel engines in planes.
Well, they're becoming increasingly popular, especially in smaller aircraft.
I could see why. I mean, diesel is usually cheaper than avgas, right?
That's one factor.
Right.
But the big thing is fuel efficiency. Compression ignition is incredibly efficient.
Ah, okay. So less fuel, lower costs, makes sense.
Plus, with all the global stuff going on right now, using readily available fuel like jet fuel or diesel is a huge advantage.
That's a great point. I hadn't even considered that. So are we going to see more diesel planes in the future then?
It's definitely possible,
Oh,
especially in smaller aircraft where fuel efficiency and flexibility are so important.
okay, interesting. So we talked about spark ignition and compression ignition. Are there any other types of engines we should know about?
Well, thinking about different engine types, I'm curious. When you hear radial engine, what comes to mind?
Oh, for me, it's those World War II planes, those big round engines. Always thought they looked so cool.
Exactly. Those are radial engines. They were really powerful for their time, with the cylinders arranged in a circle around the crankshaft.
Okay, so that circular design is what makes them radial. I get it, but why aren't they as common anymore?
But they had some drawbacks, mainly high drag, and they were pretty complex to maintain.
Ah, so not very practical for modern aircraft. Makes sense.
Exactly. Today, you're more likely to find horizontally opposed engines.
Horizontally opposed engines, what are those like?
The cylinders are arranged on opposite sides, kind of like a boxer's punches.
Ah, boxer's punches. That's a good visual. So they're more streamlined.
Yeah, exactly. Better power-to-weight ratio and a more streamlined design for less drag.
Perfect. Now, how about we get into how these engines actually work? The whole process from fuel to movement.
Right, so with spark ignition and compression ignition engines operate on a four-stroke cycle.
Four-stroke cycle. Okay, take me back to high school physics for a minute. Remind me how that works.
Sure. So each cylinder is like a tiny chamber, and the cycle starts with the intake stroke. It draws in the air and fuel mixture.
Okay, intake, that's step one, then what?
Then it's the compression stroke. The mixture gets squeezed, making it highly combustible.
Compressed air and fuel. Got it. What happens next?
That's when the power stroke happens. In spark ignition, the spark plug ignites the mixture. And in compression ignition, it self-ignites from the pressure.
Okay, power stroke. Boom. That's where the energy comes from.
Exactly. That powerful expansion pushes the piston, turning the crankshaft.
Okay, three strokes down. What's the last one?
The last one is the exhaust stroke.
Yeah.
That pushes the burnt gases out, making way for the next cycle.
Exhaust gets rid of the waste. So it's intake, compression, power, exhaust, and then repeat.
Exactly. It's happening hundreds of times per minute to keep the crankshaft turning and the propeller spinning.
Wow, that's pretty amazing when you think about it. This whole synchronized dance of air, fuel, and explosions.
It really is a marvel of engineering.
It is. Now, what about those two-stroke compression ignition engines you mentioned earlier?
Oh, right.
Mhm.
Those are definitely making a comeback. There have been some cool advancements in materials and design, making them really efficient.
So they're lighter and more powerful for their size.
Exactly. They're becoming a very attractive option for the future, especially in terms of efficiency.
I can see why. Now, before we move on to propellers, I wanted to ask about something you mentioned earlier, FADEC.
Ah, yes. Full authority digital engine control.
Yeah, FADEC. It sounds pretty high tech. What is it exactly?
Basically, It's like an autopilot for your engine.
Yeah.
It's constantly monitoring and adjusting everything for peak performance.
Really? So it controls things like fuel flow and ignition timing?
Yeah, pretty much everything. It optimizes for fuel efficiency, power, and even safety.
Wow. It's like having a dedicated co-pilot just to manage the engine. That's incredible.
Right. It's a pretty amazing system.
But with all that complexity, I have to ask, what are the downsides?
Well, the main challenge is making sure it's super robust, especially against cybersecurity threats. That's something engineers are actively addressing.
Cybersecurity threats to aircraft engines? That's not something I'd ever considered.
Yeah, it's a new frontier, really. But with everything being so connected these days, it's something we have to think about.
Absolutely. It's a reminder that as technology advances, so do the challenges.
For sure. Okay, so we've covered engines, the heart of the plane. Now, how about we talk about propellers?
Propellers. Yeah, let's get into how those translate all that engine power into actual movement.
So propellers, they're basically rotating airfoils, kind of like wings.
Hmm.
But instead of lift, they generate thrust to pull the aircraft forward.
Okay, so they're spinning and pulling the plane through the air. But I've always wondered, why are propeller blades twisted?
Ah, that's about efficiency. It's all about the angle of the blades, what we call the pitch.
Pitch, like how steep the blade is?
Right. Think of it like a fan. The tip of the blade is moving much faster than the base.
Okay, that makes sense. Different parts of the blade move at different speeds.
Exactly. So the twist ensures that each part of the blade is working at its best angle to produce maximum thrust.
So it's kind of like fine-tuning the blade for ultimate efficiency.
Exactly. Now, when it comes to propellers, there are two main types. We have fixed pitch and adjustable pitch.
Okay, so fixed pitch means the blade angle is always the same.
Right. They're simpler, lighter, and cheaper, but they're not as efficient across different phases of flight.
So it's like having one gear on a bike. It's fine for some situations, but not ideal for others.
That's a great analogy. With fixed pitch propellers, you rely on the tachometer, which measures engine RPM.
So the higher the RPM, the more power you're getting.
Yep. Now, adjustable pitch propellers, or more specifically constant speed propellers, are much more efficient.
Ugh, constant speed propellers. Those sound more advanced.
They are. They let pilots maintain a specific RPM regardless of airspeed or load, like shifting gears on a bike to maintain your pedaling speed.
So it's like an automatic transmission for the plane.
Exactly. And it's all thanks to a device called a governor.
A governor. What does that do?
It automatically adjusts the blade pitch to keep that chosen RPM. It's all about maximizing efficiency and performance.
Wow, that's pretty cool. So it sounds like pilots have more control over how the engine power is used with a constant speed propeller.
Exactly. It gives them a lot more flexibility. But, with all this talk about control and power, we got to talk about safety.
Oh, yeah, of course. What are some of the safety concerns with constant speed systems?
Well, it's really important to monitor manifold pressure with those. It tells you how much air is being forced into the engine.
Okay, manifold pressure. So like too much air could be a problem.
Right. You want to avoid overboosting. Think of it like a tire.
Yeah.
Too much air and it could burst.
Oh, I see. That makes sense. So it's all about keeping things within a safe range.
Exactly. And there was this really interesting SAIB the FAA put out a while back about propeller overspeed. It highlighted how important it is to really understand your aircraft and react properly if something unusual happens.
So even with these fancy systems, pilot awareness is still super important.
Absolutely. You always have to be on top of things, especially when you're dealing with powerful machines like aircraft.
Makes sense. All right, we've talked about engines and propellers. What's next on our systems checklist?
Well, how about the thing that makes those engines go? Fuel.
Fuel, right, the lifeblood of the plane. How does that whole system work?
So the induction system is what takes in the air, mixes it with the fuel, and then delivers that to the cylinders.
Okay, the induction system. Kind of like the fuel delivery service.
Exactly. And there are two main ways that happens: carburetors and fuel injection.
Okay, carburetors and fuel injection. I feel like I've heard of those before, but give me a refresher.
Sure. So carburetors, those are kind of the old school method. They use this system of floats and valves to regulate fuel flow based on airflow.
Carburetors. Aren't those prone to icing?
Ah, you're right, they are. And icing can be a big problem. It's basically when moisture in the air freezes inside the carburetor and blocks the fuel.
That's obviously a bad thing. What can pilots do about that?
Most aircraft with carburetors have a system for carburetor heat.
Carburetor heat, so like warming it up to prevent icing.
Yeah, it preheats the air to stop that ice from building up.
Okay, that makes sense. And it can also be used as a backup air source if the main intake gets blocked, right?
Exactly. It can be a real lifesaver in certain situations.
That's good to know, but I guess there's got to be a downside to using carburetor heat.
Yeah, the downside is that it reduces engine power.
Oh, why is that?
Well, because hot air is less dense than cold air, so you have less oxygen available for combustion.
Ah, that makes sense. So less oxygen, less power. It's a trade-off.
Right. Which is why a lot of modern aircraft use fuel injection instead.
Okay, fuel injection, that's the more modern approach, right?
Yep, exactly. It
Yeah.
injects fuel directly into the cylinders, much more precise and efficient.
So it's kind of like having a direct line from the fuel tank to each cylinder?
Yeah, you could say that. It uses an engine-driven pump, a fuel air control unit, all these components working together.
Wow, that sounds pretty complex.
It is, but it's also really effective. It reduces the risk of icing, improves fuel flow, gives you faster throttle response.
So basically, it's a more advanced and reliable system overall.
Exactly. It's a pretty big step forward in engine technology.
I can see that. But are there any downsides to fuel injection?
Well, sometimes starting a hot engine can be a bit tricky with fuel injection. And you're a bit more prone to vapor lock on really hot days.
Vapor lock.
It's when the fuel vaporizes and interrupts the flow. But
Mm.
honestly, those are pretty minor issues compared to the advantages.
Right, the pros definitely outweigh the cons. Okay, so we've talked about getting the engine running and feeding it with fuel. Now, what happens when we start climbing higher, where the air gets thinner?
Ah, that's where things get even more interesting. Thinner air means less oxygen, which means less power.
Right, just like how mountain climbers need supplemental oxygen at high altitudes.
Exactly. It's the same principle for aircraft engines.
Uh-huh.
And to combat that, we have superchargers and turbochargers.
Okay, superchargers and turbochargers, what are those exactly?
They're both systems for forced induction. Essentially, they force more air into the engine to boost power at higher altitudes.
So it's like giving the engine a little extra breath when it needs it most.
Exactly. Superchargers are like air pumps, mechanically driven by the engine. They force air into the intake manifold.
Okay, so a supercharger is like a separate component that helps the engine breathe better.
Right. Think of it like an athlete using an oxygen mask at high altitude. It helps them perform better.
That's a good analogy. And what about turbochargers? How are they different?
Turbochargers are even more efficient because they use exhaust gases to spin a turbine. And that turbine drives a compressor that forces the air in.
Whoa, so it's like using the engine's own waste to create more power?
Exactly. It's a really clever system, kind of like a recycling system for the engine.
I love that, turning waste into power. So it sounds like turbochargers are the more efficient option.
They are. But it's important to remember that with great power comes great responsibility.
Oh, I see where you're going with this. So what are the things pilots need to be careful of when using turbochargers?
Well, you have to keep an eye on oil temperature, be careful with the throttle, and make sure you follow proper cool-down procedures.
So too much boost or improper handling could damage the engine.
Exactly. It's all about understanding the limits of the system and operating it safely and responsibly.
Makes sense. Now, I remember you mentioning something called critical altitude earlier. What was that again?
Right, critical altitude. That's the maximum altitude at which a turbocharged engine can produce its rated horsepower.
So above that altitude, the engine starts to lose power.
Exactly. It's like the engine's ceiling.
Mm.
And turbochargers and superchargers help push that ceiling higher, letting aircraft operate more effectively at higher altitudes.
Got it. So it's all about maximizing performance at those higher altitudes. That's pretty amazing.
It is. Okay, so we've got air and fuel going into the engine, and
Right.
we've got systems to boost power at high altitudes. But how do we actually ignite that mixture and get the whole combustion process started?
Right. How does the engine actually come to life?
That's where the ignition system comes in. It provides the spark that sets everything in motion.
So like the spark plugs in a car engine.
Yeah, similar idea. But in aircraft, we often use magnetos.
Magnetos, what are those?
They're these self-contained devices that generate a high-voltage spark. And the cool thing is, they're completely independent of the aircraft's electrical system.
Whoa, so even if the electrical system fails, the engine can still run. That's incredible.
Yep, it's all about redundancy and safety. And to make things even more reliable, most aircraft have a dual ignition system.
Dual ignition system, so two magnetos.
Exactly, 2 magnetos, 2 spark plugs per cylinder. That way, if one magneto fails, the engine can keep running on the other one.
Wow, that's some serious redundancy. It's like having a backup generator for your engine.
I'm seeing a pattern here.
Hmm.
Safety is the top priority in aviation.
It absolutely is. Now, how do pilots actually control those magnetos?
Is there like a special switch for that?
Yeah, there's an ignition switch. It has 5 positions. O off F, R for the right magneto, L for the left, both for both, and start for engaging the starter.
5 positions. So when a pilot is doing their pre-flight checks, they test each magneto separately.
Exactly. They listen for a slight drop in engine RPM when they switch between them. It's a simple check, but it's crucial for making sure both systems are working.
So it's like a little heartbeat check for the engine, making sure both sparks are strong and healthy.
That's a great way to put it, because a malfunctioning ignition system can really ruin your day, you know? It's
Yeah.
important to catch any issues early.
That's reassuring. Now, just to be clear, is it possible for the engine to accidentally start even with the ignition off?
It is possible, though. Pretty rare. It could happen if the propeller is moved and there's some residual fuel in the cylinders. Okay, so that's why you always treat propellers with respect, even when the engine is off.
Exactly. Safety first, always.
All right, we've covered igniting the engine, but what about keeping it running smoothly? I'm guessing there's more to it than just fuel and spark.
You're right. Just like your car, aircraft engines need oil and cooling systems. Both are essential for keeping things running smoothly.
Oil, right. It's like the lifeblood of any engine. What exactly does it do?
It does a lot. Lubrication, cooling, sealing, even cleaning internal components.
Wow, it's like a multitasking wonder fluid.
You could say that.
Mm.
And there are two main types of oil systems, wet sump and dry sump.
Wet sump and dry sump, what's the difference?
Well, wet sump systems are simpler. The oil is stored right inside the engine.
Okay, so it's all self-contained. What about dry sump systems?
Those store the oil in a separate tank, and then it's circulated through the engine using pumps.
So like a central reservoir that feeds multiple components.
Exactly. It's like the difference between a small water fountain and a big recirculating pool. Both work, but the pool can handle much more water.
Okay, that's a good visual. Now, just like with fuel, you got to monitor the oil levels, right?
Yeah, absolutely.
Mm-hmm.
There's the oil pressure gauge, which tells you how much pressure the pump is generating, and the oil temperature gauge, which monitors how hot the oil's getting.
So those gauges are like the engine's vital signs.
Exactly. High oil pressure or temperature could signal a problem, so you always got to keep an eye on those gauges.
Makes sense. So what about cooling systems? Combustion generates a lot of heat. How do we keep things from overheating?
Good question. If the engine overheats, it can lead to all sorts of problems.
Hmm.
Power loss, excessive oil consumption, even catastrophic engine failure.
Yikes. Okay, so what are the solutions?
Well, the most common method in smaller aircraft is air cooling.
Air cooling, so like just using airflow to cool things down.
Yep. It utilizes air flowing over cooling fins on the cylinders.
Cooling fins, what are those?
They're like little radiators, increasing the surface area for heat to escape.
Ah, so it's all about maximizing that surface area to dissipate the heat more effectively.
Exactly. But air cooling has its limitations.
Oh, what are the downsides?
It's less effective during ground operations or when you have high power but low airspeed. And the opposite can be true too. High-speed descents can shock cool the engine.
Ah, so it's kind of a balancing act, finding the right airflow for the situation.
Exactly. And that's where pilot skill and judgment come in.
Makes sense. Are there any instruments for monitoring engine temperature?
Yeah, most aircraft have a cylinder head temperature gauge. It gives you a direct reading.
So it's like a thermometer for your engine, making sure things don't get too hot under the collar.
That's a great way to put it. The gauge usually has a green arc for normal operation and a red line for the maximum temperature.
Okay, so pilots want to stay in the green and avoid the red.
Exactly. And some aircraft even have cowl flaps.
Cowl flaps, what are those?
They're these adjustable covers that regulate airflow over the engine. It gives pilots another way to manage the temperature.
Oh, so it's like having vents for your engine.
Exactly. It's all about controlling and fine-tuning things to get the optimal temperature.
Makes sense. All right, we've talked about oil and cooling systems, keeping the engine healthy. What's next?
How about the system that gets rid of all the byproducts of combustion? The exhaust system.
The exhaust. I always thought that was just about venting those burnt gases. Is there more to it than that?
There is. It can actually provide cabin heat and defrost the windscreen, too.
Wait, really? So the heat from the exhaust is used to keep the cabin warm? That's pretty clever.
It is. It takes that otherwise wasted heat and puts it to good use.
Okay, I'm curious. How does that work?
Well, the exhaust gases first go through a muffler.
Okay, to quiet things down.
Right. And there's a shroud around the muffler that allows outside air to be drawn in and heated up by the hot exhaust.
Oh, so it's like a heat exchanger, transferring the heat from the exhaust to the outside air?
Exactly. And then that heated air is directed to the cabin or to the windscreen for defrosting.
That's pretty ingenious, turning a potential problem into a solution. But with all that hot exhaust gas flowing around, is there a risk of carbon monoxide poisoning?
You're right, that's a serious concern. Exhaust gases do contain carbon monoxide, which is odorless, colorless, and very dangerous.
Okay, so a leaky exhaust system could be a big problem.
Absolutely. Pilots need to be really careful about inspecting the exhaust system and addressing any issues right away.
Makes sense. Are there any instruments that help pilots monitor the exhaust system?
Yeah, some aircraft have an AGT gauge. It measures the temperature of the exhaust gases.
EGT gauge, what does that tell the pilot?
It gives them information about engine performance. It helps them adjust the fuel-air mixture to make sure the engine is burning fuel efficiently.
Oh, so it's like a little detective on board analyzing the engine's performance.
Exactly. And it's a really helpful tool for optimizing fuel efficiency and reducing emissions.
That makes sense. Now, you mentioned other heating systems besides using exhaust heat. What are those?
Right. So some aircraft have fuel-fired heaters or combustion heater systems.
And those use a separate burner chamber to generate heat.
Exactly. They offer a more controlled and consistent source of heat for the cabin.
Okay, so it's like a backup heating system for those extra cold days.
Exactly. And larger aircraft, like those with turbine engines, often use bleed air heating systems.
Bleed air heating.
Yeah, they use hot air that's bled off from the engine compressor section.
Ah, so it's like borrowing a little bit of the engine's heat to keep everyone warm and cozy.
Exactly. Okay, so we've talked about the engines, the propellers, the fuel system, the cooling system, and the exhaust system. What's next on our aircraft systems tour?
Well, now that we've got a good grasp of those mechanical systems, how about we dive into the electrical system?
The electrical system. Okay, let's get into it.
It's a pretty important one, right? It powers all those essential components.
It is. It's like the nervous system of the aircraft. It connects and powers everything from the lights and radios to the fuel gauges and instruments.
And even some engine components, right?
Exactly. It's what makes modern flight possible.
Okay, so it's kind of like the glue that holds everything together. What are the basics of an aircraft electrical system?
Well, most aircraft use a 14 or 28 volt DC system, similar to your car, but with a few key differences.
Okay, so it's a DC system, I get that. But what are the main components?
Well, you've got the alternator or generator, the battery, a bunch of switches, the bus bar, fuses, the voltage regulator, the ammeter or load meter, and of course, all the wiring that connects it all.
Wow, that's a lot of parts.
It is. But each one has a specific role to play. Let's start with the alternator or generator. That's your main power source during flight.
Okay, so the alternator keeps the battery charged and powers everything.
Exactly. And the battery acts as a backup power source, just like in your car.
So you have a primary power source and a backup, just in case. What about those switches you mentioned? What do they do?
Well, you have the master switch, which controls the overall electrical power, and then there are individual switches for specific components.
Okay, so pilots can turn things on and off as needed. What about the bus bar? What does that do?
The bus bar is like a central hub, a distribution point for the electrical power. It makes the wiring simpler and ensures that voltage is distributed properly.
So it's kind of like a power strip for the plane.
Yeah, that's a good way to think about it. And of course, we have fuses and circuit breaker.
To protect against overloads, right?
Exactly. They prevent damage if there's a sudden surge of electricity.
Safety first. What about those monitoring instruments you mentioned, the ammeter and load meter?
Those are really important. They show the pilot how much power is being generated and how much is being used. It's like the fuel gauge for your electrical system.
Ah, so pilots can tell at a glance if the electrical system is healthy.
Exactly. And then you have the voltage regulator, which ensures the alternator is putting out the correct voltage to keep the battery charged but not overcharged.
So it's like a babysitter for the battery, making sure it's getting the right amount of juice.
You got it. It's all about keeping the electrical system running smoothly and reliably.
All right, that was a great overview of the electrical system. What's next on our deep dive into aircraft systems?
Let's move on to the muscle of the aircraft, the hydraulic system.
Hydraulics. Okay, let's get into it. I know they're used for a lot of things, but remind me, what exactly do hydraulic systems do?
They're all about using fluid power to make things move. They power systems like the landing gear, the flaps, even some of the flight controls.
So instead of electrical motors, they use fluid pressure to move things.
Right. They're the muscles that make those systems work.
Pretty cool. What are the main parts of a hydraulic system?
Well, you have the reservoir, The pump, the filter, the selector valve, the relief valve, and the actuator or servo.
Okay, break it down for me. What does each of those do?
The reservoir holds the hydraulic fluid, the pump creates the pressure, the filter keeps the fluid clean, and the selector valve directs the flow to where it needs to go.
So the pump is like the heart of the system, and the filter is like the kidneys.
Exactly. And then you have the relief valve, which acts as a safety measure. It prevents excessive pressure from building up.
So it's like a pressure release valve on a pressure cooker.
Right. And the actuator or servo is what actually converts that fluid power into motion.
Ah, so that's what actually moves things. And speaking of fluids, what kind of hydraulic fluid do most aircraft use?
Most small aircraft use a mineral-based hydraulic fluid. And it's really important to use the correct fluid type. The manufacturer specifies which type to use.
So using the wrong fluid could be a big problem.
Definitely. Okay, how about we talk about the system that's responsible for getting us safely back on the ground, the landing gear.
Landing gear, yes. That's what makes the difference between a smooth touchdown and a, well, not so smooth landing.
Right, and when it comes to landing gear, there are two main configurations: tricycle gear and tailwheel gear.
Okay, tricycle gear and tailwheel gear, what's the difference?
Well, tricycle gear is what you see on most modern aircraft. It's got two main wheels and a nose wheel.
Ah, so that's the standard setup. What are the advantages of tricycle gear?
It's got better braking at high speeds, better forward visibility for the pilot, and it's generally more stable on the ground. Makes it easier to handle.
So it's the safer and more forgiving option for pilots, especially beginners.
Exactly. Now, tailwheel gear is the older style. It's got two main wheels and a tail wheel.
So the small wheel is at the back instead of the front. When would you use that kind of configuration?
You'd see it more on older aircraft or those designed for rough fields. Think like bush planes.
Okay, so tailwheel gear is more rugged.
Yeah, it's definitely more suited for those challenging environments, but it can be trickier to handle on the ground.
Oh, why is that?
Well, you have less forward visibility, and there's a higher risk of ground looping if you're not careful. It takes more skill to handle.
So it's not for the faint of heart.
You could say that. But for those who master it, it can be a really rewarding experience. Now, besides the configuration, landing gear can also be fixed or retractable.
Oh, right, I remember that. Fixed gear means the wheels are always out.
Yep. It's simpler, more reliable, and requires less maintenance.
But creates more drag, right?
Exactly. It slows the aircraft down and makes it less fuel efficient.
So it's like having those mud flaps on your truck. They're great for off-roading, but not so great for fuel economy.
Perfect analogy. Now, retractable gear is tucked away during flight.
So it's hidden away to make the aircraft more aerodynamic.
Exactly. It reduces drag and improves fuel efficiency.
Hmm.
But it also adds complexity to the system.
So it's a trade-off, simpler design versus better performance.
Exactly. Now, let's not forget about brakes.
Right, brakes. How do those work on an aircraft?
They're usually located on the main wheels.
Yeah.
And they can be operated by hand or foot pedals, depending on the aircraft.
Okay, so hand control of foot pedals. What about steering? How do you steer a plane on the ground?
Well, we have differential braking.
Differential braking. What's that?
It means you can apply more brake force to one wheel than the other.
Host speaker.
Exactly.
Yeah.
It means you can apply more brake force to one wheel than the other.
Okay, so why would you want to brake more on one side?
It's all about steering on the ground, especially at low speeds.
Ah, I see. So differential braking helps you make tighter turns.
Exactly. It's super helpful when you're taxiing around the airport.
It's like having power steering for the plane.
You got it. All right. We've covered the landing gear. That gets us safely back on the ground. But how about those high-flying adventures at, like, 30,000 feet? How do we survive up there where the air is so thin?
Yeah, good point. I mean, I know we need oxygen to breathe, but how does that work in a plane?
Well, that's where pressurization and oxygen systems come in.
Pressurization. So, like, making the cabin environment more like it is at lower altitudes?
Exactly. Pressurization systems maintain a comfortable, breathable environment even when you're cruising at high altitude.
Okay, so how does that work? Do they, like, pump in air from outside?
They use bleed air from the engine compressors, usually. Or in older aircraft, they might use superchargers.
Bleed air. So they take air from the engines and use that to pressurize the cabin.
Yep. And they maintain a pressure that's roughly equivalent to about 8,000 feet, even if you're flying much higher.
Oh, wow. That's pretty amazing. So it's like you're bringing a bit of that lower altitude air up with you.
Exactly. And to regulate the pressure, there's an outflow valve.
An outflow valve. So it releases excess air if the pressure gets too high.
Exactly. It's kind of like a pressure relief valve.
Yeah.
Now, of course, you have instruments to monitor all this.
Oh, yeah. Instruments are super important in aviation. So what kind of instruments are used for the pressurization system?
Well, you have the cabin differential pressure gauge. That shows the difference between the cabin pressure and the outside air pressure.
So pilots can see if the pressurization is working correctly?
Exactly. And then there's the cabin altimeter, which shows the equivalent altitude of that cabin pressure. And the cabin rate of climb indicator shows how quickly the pressure is changing.
Wow, so it's like having a little weather station for the cabin environment, making sure everything is safe and comfortable.
You got it. Now, even with pressurization, supplemental oxygen might be needed at those higher altitudes.
Ah, right. Because even at 8,000 feet, the air is still thinner than it is at sea level.
Exactly. Supplemental oxygen systems are there to prevent hypoxia.
Hypoxia. That's when your body doesn't get enough oxygen, right?
Right. It can lead to all sorts of problems, dizziness, confusion, even unconsciousness.
Yeah, that's definitely something you want to avoid, especially when you're flying a plane.
You got it. And there are different types of oxygen systems. Continuous flow, diluter demand, pressure demand. Each one delivers oxygen in a different way, depending on the altitude of the situation.
Okay, so different systems for different scenarios. What about those oxygen masks you see in the safety briefings? When would those be used?
Those would be used if the cabin pressure suddenly drops for some reason, or if you're flying at an altitude where supplemental oxygen is required.
Okay, so they're like an emergency backup system.
Yeah, exactly. They ensure that everyone can still breathe, even if the cabin environment is compromised.
Makes sense. All right, so we've got pressurization and oxygen systems keeping us breathing at high altitude. What about those icy encounters you sometimes hear about?
Ice. That's where anti-ice and de-ice systems come in.
Anti-ice and de-ice. So one prevents ice from forming and the other removes it.
You got it. And they're both super important for flying safely in certain conditions. Imagine flying through a cloud and suddenly ice starts building up on your wings. Not a good situation.
Yeah, that doesn't sound good. Ice can really mess with the aerodynamics, right?
Absolutely. It disrupts airflow, reduces lift, and increases drag. Can make controlling the aircraft really difficult.
Okay, so let's talk about how to combat that ice. First up, de-ice systems.
De-ice systems are for getting rid of ice that's already formed. And one of the most common ones is the inflatable de-icing boot.
Oh, de-icing boots. I think I've seen those. They're like rubber coverings on the wings, right?
Exactly. They're usually found on the leading edges of the wings and other surfaces. When they inflate, they crack and dislodge the ice.
So they kind of give the wing a good shake to knock the ice off.
That's a good way to think about it. And pilots cycle them on and off as needed based on the conditions.
So they're not constantly inflating and deflating.
Right. They just use them when they need to. And it's important to note, there's no need to wait for a lot of ice to build up before using the boots.
So if you see ice, cycle the boots.
Exactly. Better safe than sorry. Now, some aircraft have a different system. The weeping wing.
Weeping wing? What's that?
It's pretty cool. It distributes an anti-freeze solution through tiny holes in the leading edge of the wing.
So it's constantly weeping antifreeze to prevent ice from forming.
Exactly. It's like giving the wing a protective coating to keep the ice away.
That's pretty high tech. Now, what about the windscreen? I imagine ice on the windscreen could be a big problem.
You're right. You got to be able to see where you're going. Most aircraft have systems for windscreen anti-ice.
So how do those work?
They can be alcohol-based or electrically heated. Both are effective at keeping the windscreen clear.
Oh, I've seen those heated windscreens in action. It's amazing how quickly they clear the ice. It's like magic.
They're pretty impressive, right? And of course, we can't forget about the propellers.
Right. Propellers are spinning out there in the elements, too. They must be prone to icing as well.
They are. That's why they often have alcohol or electrically heated elements, including propeller anti-ice boots.
Oh, wait, they have boots for the propellers, too.
Yep. And those boots are designed to cycle in sections, distributing heat evenly.
Why is it important to distribute the heat evenly?
Well, it prevents uneven loading on the propeller, which can cause vibration and potentially damage the propeller.
That makes sense. It's all about balance and keeping things running smoothly.
Exactly. It's really amazing how much engineering and thought goes into preventing and removing ice on an aircraft.
It is. It's clearly a top priority. Now, we've talked about all these different systems. Engines, propellers, fuel, cooling, exhaust, electrical, hydraulic, landing gear, pressurization, oxygen, anti-ice, de-ice. It's a lot to take in.
It is. But it all works together to make this incredible feat of flight possible. And, before we go any further, I think it's important to step back and talk about the fundamental forces that actually allow an aircraft to fly.
Oh, yeah, good point. All those systems are great, but they wouldn't do much good if we didn't understand the basics of aerodynamics.
Exactly. It's like having a powerful car, but not knowing how to drive. You need to understand the rules of the road, or in this case, the rules of the sky.
So aerodynamics is like the language of flight.
Exactly. It's all about how air interacts with objects, and specifically how we can use that interaction to achieve flight.
Okay, so let's talk about the key players in aerodynamics. I know you've mentioned airfoils before, but give me a refresher. What exactly is an airfoil?
An airfoil is the shape of a wing, or any surface designed to create lift when it moves through the air. Think about a bird's wing or the cross-section of an airplane wing.
Right, that classic curved shape.
Exactly. And that shape is super important. It has a curved upper surface and a relatively flat lower surface.
Okay, so that curved shape is what makes it an airfoil. But why is that shape so crucial for flight?
Because it creates a difference in air pressure. The air flowing over the top of the wing has to travel a longer distance than the air flowing underneath.
Okay, the air on top travels farther, so what? Why is that important?
Well, since the air on top has to travel farther in the same amount of time, it has to move faster. And faster moving air creates lower pressure. It's Bernoulli's principle.
Bernoulli's principle. Okay, I remember learning about that in physics class, but I'm a little fuzzy on the details. Can you remind me how it works?
Imagine you're holding a piece of paper horizontally in front of your mouth, and you blow over the top of it.
The paper lifts up. I used to do that all the time as a kid.
Exactly. That's Bernoulli's principle in action. You're creating faster moving air over the top of the paper, which lowers the pressure. The higher pressure underneath pushes the paper up.
Okay, that makes sense. So it's the same principle with airplane wings. The faster moving air on top creates lower pressure, and that creates lift.
Exactly. And that difference in pressure between the top and bottom of the wing is what creates the lift force that keeps the aircraft airborne.
So it's not just the engines pushing the plane forward, it's this clever manipulation of air pressure over the wings that's doing the heavy lifting.
You got it. The engines provide the thrust to move the plane forward, and that creates the airflow over the wings. Then the shape of the wings generates the lift that overcomes gravity.
It's like a beautiful symphony of physics and engineering working in harmony to make flight possible.
That's a great way to put it. Now, another important factor in generating lift is the angle of attack.
Angle of attack, what's that?
It's the angle between the wing and the oncoming airflow. Basically, how much the wing is tilted upward.
Okay, so if the wing is tilted up more, the angle of attack is higher.
Exactly. And as the angle of attack increases, so does the lift. But there's a limit. If it gets too high, the airflow over the wing can become turbulent and separate from the wing.
And what happens then?
That's called a stall. It results in a sudden loss of lift.
A stall? That sounds pretty dangerous. How do pilots know if a wing is about to stall?
Well, they're trained to recognize the signs. A mushy feeling in the controls or a buffeting vibration. They also have instruments that help them monitor airspeed and angle of attack.
So it's all about staying within a safe operating range.
Exactly. Maintaining that balance between generating enough lift and avoiding a stall.
Okay, so we've talked about lift. Now what about the force that's working against us?
Drag.
Drag. The force that opposes motion through the air. It's what slows the aircraft down and makes it work harder to fly.
So lift is what gets us off the ground, and drag is trying to pull us back down. In a way, yes. Drag is kind of like friction for the air, and unavoidable. But there are different types of drag, and understanding those helps us design more efficient aircraft.
Okay, so what are the main types of drag?
Well, first, we have parasite drag. It's caused by the friction of air moving over the aircraft's surfaces.
So the smoother the surface, the less drag.
Exactly. Think of a fighter jet compared to a cargo plane. The fighter jet's sleek design cuts through the air much more efficiently.
Right, because it has less surface area for the air to rub against.
Exactly. Now, the other type of drag is induced drag. And this one's a bit trickier. It's actually a byproduct of lift.
So the more lift you create, the more induced drag you get.
You got it. It's caused by those swirling vortices of air that form at the wingtips.
Wingtip vortices, I've seen those trailing behind planes, especially on humid days.
Yep, those are the ones. And those vortices create drag, pulling the aircraft backward.
So it's a trade-off. You need lift to stay airborne, but that lift also creates drag.
Right, it's a constant battle. But there are ways to minimize induced drag. One way is to use wingtip devices, like winglets.
Winglets, those are the little fins you see on the tips of some wings, right?
Exactly. They help reduce the strength of those wingtip vortices, making the aircraft more efficient.
So it's like they're smoothing out the airflow, reducing that drag.
That's a good way to think about it. All right, so we've covered lift and drag, those fundamental forces that govern flight. But how do pilots actually control the aircraft? How do they steer and maneuver it through the air? Well, for that, we have control surfaces. They're hinged sections on the wings and tail that the pilot can move to change the aircraft's attitude and direction.
Okay, so they're kind of like the steering wheel and pedals of the plane.
That's a good analogy. There are three primary control surfaces: the ailerons, the elevator, and the rudder.
Okay, three control surfaces. What does each one do?
The ailerons are on the outer trailing edges of the wings. They control roll, which is the aircraft's movement around its longitudinal axis.
Roll, so like tilting the wings left or right.
Exactly. And moving the ailerons causes the aircraft to bank, just like leaning into a turn on a motorcycle.
Okay, ailerons for banking. What about the elevator?
The elevator is on the horizontal stabilizer at the tail. It controls the aircraft's pitch.
Pitch, so like pointing the nose up or down.
Exactly. Moving the elevator up causes the nose to pitch up, and moving it down causes the nose to pitch down.
Okay, so ailerons for banking, elevator for pitching. What about the rudder?
The rudder is on the vertical stabilizer at the tail, and it controls yaw.
Yeah.
Yaw is the aircraft's movement around its vertical axis, so like swinging the nose left to right.
Ah, I see. So the rudder is kind of like the rudder on a boat?
Exactly. It's used to keep the aircraft pointed in the right direction.
So by coordinating all three of these control surfaces, pilots can maneuver the aircraft however they need to.
Precisely. It's a three-dimensional dance, really.
That's amazing. And how do pilots actually control those surfaces?
They use a control yoke or joystick for roll and pitch, and rudder pedals for yaw.
It sounds almost like playing a video game.
You could say that. Now, in addition to those primary control surfaces, some aircraft also have secondary control surfaces.
Secondary control surfaces? Like what? You have flaps and spoilers.
Oh yeah, flaps. Those are the things that come out of the wings during takeoff and landing, right?
You got it. Flaps are extensions on the trailing edge of the wings. They increase lift and drag, which lets the aircraft fly slower.
Ah, so they help the aircraft take off and land at lower speeds.
Exactly. And then there are spoilers.
Spoilers. Those are the things that pop up in the wings, right?
Yeah.
But don't they reduce lift? Why would you want to do that?
Well, spoilers have a few different uses. They can be used to help the aircraft descend more quickly, or to reduce lift after landing, which lets the brakes work more effectively.
Okay, so flaps help the plane fly slower, and spoilers help it slow down faster. It's all about control.
You got it. They're both important for those critical phases of flight. Now let's talk about stability.
Stability. Yeah, that's pretty important when you're flying through the air. What exactly does it mean for an aircraft to be stable? It means that the aircraft wants to return to its original flight path if something disturbs it, like a gust of wind or a change in control inputs.
So it's kind of like a self-correcting mechanism.
Exactly. And there are three types of stability: static, dynamic, and directional.
Okay, break it down for me. What's the difference between those three?
So static stability is about the aircraft's initial tendency to return to its original position after a disturbance. Think of it like a ball in a bowl. If you push it slightly, it rolls back to the center.
Okay, so it wants to stay balanced.
Exactly. Now, dynamic stability is about how smoothly it returns to that original position. Does it oscillate back and forth, or does it smoothly settle back down?
So it's not just about going back, it's about how gracefully it gets there.
Right. And then there's directional stability. That's about the aircraft's tendency to maintain a straight flight path. If you let go of the controls, does it naturally want to fly straight, or does it want to yaw left or right?
So a stable aircraft is predictable and easy to control.
Exactly. And stability is all about careful design. The shape of the wings, the tail, the center of gravity, it all plays a role.
It's a lot to consider.
It is. Aircraft designers put a lot of thought into making sure an aircraft is stable, but also maneuverable.
So it's a balance between those two things. Okay, so we've talked about stability. Now, how do pilots actually use all of this to maneuver the aircraft through the air?
Well, they use a combination of control inputs, their knowledge of aerodynamics, and their situational awareness.
So it's a mix of skill, knowledge, and experience.
Exactly. And when it comes to basic maneuvering, we can break it down into 4 categories: straight and level flight, turns, climbs, and descents.
Okay, the 4 fundamentals of flying. Let's start with straight and level flight. What's involved in that?
Straight and level flight is all about maintaining a constant heading, altitude, and airspeed. It's the most basic maneuver.
Sounds simple enough, but I imagine it's not as easy as it sounds.
Right. It requires making constant small adjustments to the controls to counteract any disturbances.
So you're always making little tweaks to keep the plane flying smoothly.
Exactly. Now, what about turns? How do you make a plane turn?
Well, I know you use the ailerons to bank the wings.
You're right, you do. But it's also about coordinating the rudder to prevent slipping or skidding.
So it's a coordinated movement.
Exactly. You want a smooth, controlled turn.
Okay, so you use the ailerons to bank the wings into the turn, and the rudder to keep the nose aligned with the direction of travel.
You got it. Now, what about climbs and descents?
Well, I know you use the elevator to pitch the nose up or down.
You're right, you do. But it's also about managing the engine power. To climb, you increase power and pitch the nose up. To descend, you reduce power and pitch the nose down.
So it's a combination of power and pitch to control your altitude.
Exactly. And it's important to make those changes gradually and smoothly for a comfortable ride.
Smoothness is key. All right, so we've got maneuvering down. But what about getting from point A to point B? How do pilots navigate and make sure they're going in the right direction?
Navigation. That's a whole other world. Pilots use a variety of techniques. We have traditional methods like pilotage and dead reckoning, and then modern technology like GPS.
Okay, let's start with the old school methods. Pilotage and dead reckoning. Those sound like something out of a pirate movie.
They are pretty old school, but they're still important, especially as backup systems. Pilotage is all about visually identifying landmarks on the ground, comparing them to a map or chart.
So it's like using a road map, but for the sky.
Exactly. You're looking for familiar landmarks to confirm your position and make course corrections if needed. Now, dead reckoning is a bit more mathematical. It involves calculating your position based on your known starting point, speed, and heading.
So you're estimating your position based on time, speed, and direction.
Right. And you have to factor in things like wind drift, which can push you off course. And then, of course, there's GPS.
GPS, the modern navigator's best friend.
Exactly. GPS uses satellites to determine your exact position. It's revolutionized navigation.
It's like having a digital co-pilot that always knows where you are.
You got it. Now, another important factor in aviation is weather.
Weather, yeah. That's something you can't really control. How do pilots deal with changing weather conditions, especially when they're already up in the air?
Well, they use a variety of resources to stay informed. Weather reports, forecasts, radar. They're constantly monitoring the situation.
So it's like checking the weather forecast, but much more critical.
Right. Because weather can affect everything.
Mm.
Visibility, turbulence, wind conditions, icing. It can make a huge difference in how a flight goes.
I can imagine. So pilots need to be prepared to adjust their plans based on the weather.
Exactly. They might need to alter their course, delay their flight, or even cancel it if the weather's too bad.
Safety first, always.
Absolutely. Now, another important aspect is communication.
Communication, yeah. Pilots need to be able to talk to each other and to air traffic control, right?
Right. Communication is key for safety. Aircraft are equipped with radios.
So they can talk to air traffic control and to other planes.
Exactly. Air traffic control helps guide aircraft safely through airspace, prevents collisions, and helps them land safely at airports.
So they're like the traffic cops of the sky, keeping everything organized and running smoothly.
You got it. And pilots also use their radios to communicate with each other, especially when they're flying in areas without air traffic control coverage. It's like a courtesy call, letting other pilots know your position and intentions.
So it's a combination of guidance from air traffic control and direct communication between pilots.
Exactly. It's all about working together to keep the skies safe.
Okay, we've covered navigation, weather, and communication. Now, what about the actual process of flying? What are the different phases of a typical flight?
Well, we can break it down into 7 main phases: pre-flight, takeoff, climb, cruise, descent, approach, and landing.
7 phases. So it's like a journey with different stages, each with its own challenges and procedures.
Exactly. Let's start with pre-flight. That's all about preparation.
Okay, pre-flight. So like getting everything ready before you even start the engine.
Yeah, right. It involves inspecting the aircraft, checking the weather, planning the route, calculating fuel requirements, making sure everything is in order.
So it's like packing your bags, checking the map, and making sure your car is in good working order before you head out on a road trip.
Perfect analogy. It's all about minimizing risks and ensuring a safe and successful flight.
And then comes the exciting part, takeoff.
Takeoff. That's all about getting the aircraft airborne safely and efficiently.
I can imagine there's a lot involved in that.
There is. It involves lining up the aircraft with the runway, applying power, using the controls to lift it off the ground at the right speed and angle.
Sounds like a delicate balance of power, speed, and control.
It is. And it requires a lot of skill and training.
So once you're off the ground, what's next?
Next is the climb. That's where the pilot increases altitude to reach the desired cruising level.
And that involves managing power, pitch, and airspeed.
Right, exactly. It's about making a smooth and efficient climb.
So it's like driving up a mountain road, gradually gaining elevation while maintaining a safe and comfortable speed.
Perfect analogy. And once you reach your desired altitude, you enter the cruise phase.
Ah, the cruise phase. That sounds relaxing. Just cruising along, enjoying the view.
It can be. It's typically the longest phase of the flight. The aircraft flies at a relatively constant altitude and airspeed.
So it's like cruising down the highway, maintaining a steady speed.
Exactly. But even during cruise, the pilots are still working, monitoring instruments, communicating with air traffic control, making adjustments to maintain course and altitude.
So always staying vigilant. What happens when it's time to start heading back down?
That's the descent phase. The pilot reduces power and pitches the nose down, initiating a gradual descent.
Okay, so the opposite of climbing, reducing power and pitching down.
Exactly. And as you get closer to your destination, you enter the approach phase.
The approach phase, that's where things start to get a little more intense again, right?
It is a critical phase for sure. It involves aligning the aircraft with the runway and preparing for landing.
Okay, so it's like getting off the highway and navigating those local roads to your final destination.
Exactly. And finally, we have the landing phase.
The landing, the moment of truth. What's involved in bringing that aircraft safely back down to the ground?
It involves reducing airspeed, extending the flaps, and making precise control inputs to touch down smoothly on the runway.
So it's like parking your car in the garage, bringing the journey to a smooth and successful conclusion.
That's a great analogy. And landing is definitely one of the most challenging aspects of flying, requiring a lot of skill and practice.
It's the grand finale of the flight.
Exactly. Okay, we've covered a lot of ground here, from the basic forces of flight to the different phases of a typical flight. It's amazing how much goes into getting an aircraft safely off the ground and back down again.
It really is. And behind all these incredible machines and systems are the people who make it all possible. The pilots, the air traffic controllers, the engineers, the mechanics.
Absolutely. It's a whole community of dedicated and passionate individuals who work together to make this incredible feat of human flight a reality.
So let's talk about those people. What are the qualities that make a great pilot?
Well, pilots are a special breed. They need a unique combination of skills, knowledge, and personality traits. They need to be skilled in handling the aircraft, knowledgeable about all the systems and procedures, and able to make quick decisions under pressure. They also need to be calm, cool, and collected, even in challenging situations.
And I imagine they go through rigorous training.
Oh, absolutely. Their training is extensive and demanding. It covers everything from aerodynamics and meteorology to navigation, communication, and emergency procedures. They spend countless hours in the classroom and in sophisticated flight simulators, honing their skills and preparing for every imaginable scenario.
It sounds like a really challenging and rewarding profession.
It is. It's a huge responsibility, but it's also an incredible privilege to be able to fly and to experience the world from that unique perspective.
And what about air traffic controllers? They play a vital role in keeping the skies safe, too.
Absolutely. Air traffic controllers are like the guardians of the skies. They're the ones who guide aircraft safely through airspace, preventing collisions, and ensuring everything runs smoothly. They work in high-pressure environments, constantly monitoring radar screens, communicating with pilots, and making critical decisions that affect the lives of countless people.
It sounds like a really demanding job.
It is. They need to be incredibly focused and detail-oriented, with the ability to think several steps ahead and anticipate potential problems. They're the unsung heroes of aviation, playing a vital role in keeping us all safe.
And then there are the engineers who design and build these incredible flying machines.
The engineers. They're the masterminds behind it all. They're constantly pushing the boundaries of technology and innovation, coming up with new designs and solutions to make aircraft safer, more efficient, and more environmentally friendly.
They're like the architects of the sky.
Exactly. They have to have a deep understanding of aerodynamics, material science, and a whole host of other disciplines. And they have to be incredibly creative and problem solvers, because designing and building an aircraft is no easy feat.
It's amazing to think about all the different people who contribute to making flight possible.
It really is. It's a team effort, from the pilots and air traffic controllers to the engineers and mechanics and everyone in between.
And of course, we can't forget the flight attendants who take care of us once we're on board.
The flight attendants are amazing. They're the ones who make sure we're comfortable and safe during the flight. They're trained to handle all sorts of situations, from helping passengers with their bags to dealing with medical emergencies, They're true professionals.
And they always do it with a smile.
Exactly. They play a crucial role in making air travel a more pleasant and enjoyable experience.
It's a reminder that aviation is about so much more than just machines and technology. It's about people. People with a passion for flight, a commitment to safety, and a desire to connect the world.
Well said. Now let's talk about why we fly. What is it about flight that captures our imaginations and makes it such a compelling experience?
It's a good question. I think it's that feeling of freedom, that sense of wonder and awe that you get when you're soaring above the earth. It's like you're breaking free from the constraints of gravity and experiencing the world from a whole new perspective.
You're right. There's something magical about flight. It allows us to travel to distant lands, connect with people from all over the world, and experience cultures that are different from our own. It broadens our horizons and expands our understanding of the world.
It's also a reminder of the incredible ingenuity and determination of the human spirit. We dreamed of flying for centuries, and eventually we made it happen. It's a testament to our ability to overcome challenges and achieve the seemingly impossible.
I agree. And flight continues to evolve and inspire us. From the early pioneers who dared to dream of flying to the modern-day innovators who are pushing the boundaries of aviation technology, we continue to strive for new heights and explore new possibilities.
It's a story that's still being written, and I, for one, can't wait to see what the future holds for aviation.
Me too. It's an exciting time to be a part of this incredible industry.
It is. Well, folks, we've covered a lot of ground today. We've explored the inner workings of aircraft, delved into the history and future of flight, and celebrated the people who make it all possible. I hope you've enjoyed this deep dive into the world of aviation.
It's been a pleasure sharing this journey with you. And remember, the next time you're on a plane, take a moment to appreciate the amazing symphony of technology, human ingenuity, and sheer determination that's making it all happen.
Well said. Thanks for joining us on this adventure. Until next time, keep your eyes on the skies.
It did. The Wright brothers' success. It was the culmination of years of research and experimentation. They studied their predecessors, built gliders, developed a lightweight engine and propeller system.
And their invention, this biplane, it had a 40-foot wingspan, weighed just over 600 pounds.
Yeah, and it made 4 flights that day. The longest, only 59 seconds, covering 852 feet.
Wow, that's pretty amazing to think about. It was just a small step, but it sparked a revolution in technology.
Absolutely. And from there, aviation just took off,
Hmm.
driven by all those new technologies and the demand for faster, more efficient aircraft.
Right, and then World War I happened. That really pushed the development of military aircraft, didn't it?
Yeah, it did. The demands of war led to more powerful engines, better designs, more effective weapons.
So even though war is a terrible thing, it often drives innovation.
It does. It pushes us to find solutions to improve technology. And after World War I, we saw a shift towards civilian aviation.
Right, with the rise of airlines and airmail services, people started to see the potential of flight for connecting the world.
Exactly. And in the 1920s and 30s, those legendary pilots, like Charles Lindbergh, Amelia Earhart, Wiley Post, they really captured the imagination.
Oh, absolutely. Lindbergh's solo flight across the Atlantic, that was a huge moment for aviation.
It was. It showed what was possible with airplanes, and then Amelia Earhart, her attempt to fly around the world, it was inspiring, even though it ended tragically.
It showed that anything is possible if you have the courage to pursue your dreams.
Exactly. And Wiley Post flights around the world, they showed how far aviation had come,
Yeah.
how capable those aircraft were becoming.
These pioneers, they really paved the way for the future of flight.
They did. And then World War II came along, and that led to even more advancements like jet engines and radar.
Jet engine, that was a game changer for aviation.
Oh, absolutely. It opened up a whole new era of speed and performance. And after the war, the jet age really took off.
With commercial airlines adopting jets, shrinking travel times, making flying more accessible.
Exactly. And then in 1958, we saw the introduction of the Boeing 707, the first commercially successful jetliner.
The 707, it revolutionized air travel.
It did. And then, of course, there was the Concorde, the supersonic passenger jet.
The Concorde, that was a marvel of engineering.
It was. It could travel at twice the speed of sound.
Imagine flying from New York to London in just a few hours.
It was incredible. But the operating costs were high, and eventually it was retired.
Still, it's an iconic symbol of the supersonic era.
Absolutely.
Yeah.
Now, in recent decades, The focus has shifted towards efficiency, safety, and sustainability.
Right, we're seeing more fuel-efficient aircraft, better navigation systems, advanced safety features.
Exactly. The Boeing 787 Dreamliner, for example.
Yeah.
It's a great example of modern aircraft design.
It's incredibly fuel efficient.
And then the Airbus A380, the world's largest passenger airliner, that shows just how much capacity and efficiency we can achieve.
It's amazing how far we've come. And the future of flight. It's pretty exciting, too.
Oh, it is. We have electric propulsion, new supersonic designs, autonomous flight.
Yeah, those electric aircraft, they're starting to make some real progress, aren't they?
They are. They're quieter, cleaner, and more efficient. They could really change the game for short-haul flights.
And what about supersonic travel? Will we ever see a return to those days of flying faster than sound?
I think we will. Companies are working on new supersonic designs that are more fuel efficient and quieter than the Concorde.
So supersonic travel could become more accessible and sustainable.
It could. And then there's a whole world of autonomous flight with drones.
Drones are already changing so many industries.
They are. And the possibilities are pretty much endless. And for those who dream of even faster travel, there's hypersonic travel.
Hypersonic travel, flying at 5 times the speed of sound or more.
Exactly. Imagine traveling from New York to Tokyo in just a couple of hours.
That's mind-blowing. But with all this talk of future technology, it's important to remember the key factors that will shape the future of aviation.
You're right. Sustainability and accessibility.
Yeah.
They need to be at the forefront of everything we do.
Absolutely. How can we ensure that aviation becomes more sustainable, minimizing its impact on the environment?
Well, it's going to take a lot of work, a lot of collaboration. The industry is developing more efficient aircraft, exploring alternative fuels, working on better air traffic management systems.
So it's a multi-pronged approach.
It is. And we also need to make sure that flight is accessible to everyone, regardless of their abilities.
Right. Everyone should have the opportunity to experience the wonder of flight.
I agree. And the industry is making progress in this area, making aircraft and airports more accessible for people with disabilities.
That's great to hear. So the future of flight, it's looking bright, filled with possibilities?
It is a future where we can connect people and cultures in a way that's safe, sustainable, and accessible to all.
Now, before we wrap up, I want to touch on one more important aspect. Aircraft instruments.
Aircraft instruments, right. They're like the dashboard of the plane, giving the pilot all the information they need.
Exactly. They're essential for a safe flight. Can you break down some of the key instruments for us?
Sure. There's the 6-pack. That's what we call the primary flight instruments.
The 6-pack. Okay, what are those?
Well, there's the airspeed indicator, the altimeter, the vertical speed indicator, the attitude indicator, the heading indicator, and the turn coordinator.
6 essential instruments, all working together. What does each one do?
The airspeed indicator tells you how fast you're going through the air. The altimeter tells you your altitude. The VSI tells you how quickly you're climbing or descending. The attitude indicator shows you your orientation relative to the horizon. The heading indicator shows your direction of travel. And the turn coordinator tells you about your turn rate and coordination.
Wow, that's a lot of information to process.
It is. But pilots are trained to interpret all those instruments and use that information to fly the plane safely. Now, in addition to the 6-pack, there are other important instruments, like the tachometer, which tells you the engine RPM.
So it's a measure of engine power.
Exactly. And the manifold pressure gauge, which tells you how much air is being forced into the engine.
So it's like a boost gauge.
Exactly. And of course, you have instruments for monitoring fuel levels, oil pressure and temperature, electrical system performance, all that good stuff.
So it's like a whole orchestra of instruments, each playing its part to keep the plane flying safely and smoothly.
You got it. And we're seeing more and more aircraft with glass cockpits.
Oh yeah, glass cockpits. Those are pretty cool. They replace those traditional analog instruments with digital displays, right?
Exactly. They can show way more information in a more user-friendly way.
Yeah.
It makes things easier for the pilots.
So it's like having a super high-tech dashboard with all the information you need right there in front of you.
You got it. And as technology advances, those glass cockpits are becoming even more sophisticated.
That's amazing. Technology really is changing the game for aviation.
It is. And speaking of technology, I think it's important to talk about how all of this has contributed to making aviation one of the safest forms of transportation in the world.
Safety. Yeah, that's a big one. What are some of the key factors that have made flying so safe?
Well, it starts with the design of the aircraft themselves. Modern aircraft have multiple layers of redundancy built in. That means that if one system fails, there's a backup system ready to take over.
Okay, so redundancy is key. It's like having a safety net.
Exactly. And then there's the rigorous testing and certification process that all aircraft have to go through.
So they're put through the ringer to make sure they meet the highest safety standards.
Absolutely. And maintenance is another big one. Aircraft are constantly being inspected and maintained to make sure everything is in tip-top shape.
So it's all about prevention and early detection.
Right. Catching problems before they become serious issues. And then, of course, there's pilot training. Pilots undergo incredibly extensive training to make sure they're prepared for anything.
So it's not just about knowing how to fly a plane, it's about understanding all the systems, the weather, the regulations, everything.
Exactly. And then we have operational procedures. These are standardized procedures that airlines and other organizations use to minimize risks.
So it's all about having a system in place, a culture of safety that everyone follows.
You got it. And those procedures are constantly being updated and improved based on lessons learned from past incidents.
So it's a constant process of learning and adapting.
It is. The goal is to make flying as safe as possible. And despite the fact that accidents do happen, aviation has a remarkably good safety record.
It's a testament to the hard work and dedication of everyone involved in this industry.
It really is. Well, I think we've covered just about everything. We've talked about the intricacies of aircraft systems, the history and future of flight, the people who make it all possible.
It's been an amazing journey.
It has. And it's important to remember this is just the beginning.
There's always more to explore and learn about aviation.
Absolutely. So stay curious, keep asking questions, and never lose that sense of wonder.
And next time you see a plane flying overhead, take a moment to appreciate everything that went into making that flight possible.
The engineering, the technology, the human spirit of adventure, it's all quite incredible.
Well said. Thanks for joining us on this deep dive into the world of aviation.
It's been my pleasure. Until next time, happy flying.